Make sure your phones and all that is put away now. I can't compete with that. I can't compete with Justin Bieber. I just can't. Anyways, who listens to Justin? Oh, you'd be surprised. Right. State the theoretical probability of the coin landing on tails. This is on 29. Okay, theoretical, we think of the coin, right? Heads or tails. So in this case, the theoretical probability, we actually go TP here just to differentiate, of landing on tails would be 1 over 2. 2 options in total, okay? Or 50%, that's okay. State the experimental probability. Here we actually look at what was the outcome, and this will vary greatly, right? How I present that to you. So experimental probability of landing on tails would be 240 over, I would actually show this, okay, that I'm adding the two numbers, so it's 240 over 400 is my experimental probability. If you toss the coin 1,000 times, how many times would you expect it to land on tails? Do not use experimental probability. Okay, we're making a prediction. So we're going to go 1 over 2, right? Because, folks, the reason this isn't quite half yet is because you need to toss it more times. Okay, once you start tossing something 1,000 times or more, these two should be very close, right? But they aren't right now. So we're going to use the theoretical like that. So 500 times. Okay, 500 times. Use TP, right? A few exclamation marks so you don't miss it. So when you know both, you use theoretical, okay? Next. Deck of cards. Okay? So Megan draws 5 cards from a standard deck of cards. Every time she pulls a card, she records the results and then places it back, okay? If you don't place something back, it changes. That's what the next concept is going to talk about. State the theoretical probability of drawing a 6 of spades. So theoretical probability, bless you. We know this is going to be 52 cards, okay? When it's theoretical, we think of our deck of cards, right? This is going to backfire, I know already. I'm not really good at drawing, okay? Cards. Okay, this is the deck. You think of the deck because it's in theory. So how many 6 of spades do you have in a deck of cards? I don't know. Well, there's 4 6s, right? 6 of diamonds, 6 of hearts, 6 of spades, 6 of clubs, right? So there's only one 6 of spades, right? So that goes there. Next, state the experimental probability of drawing a 6 of spades. So experimental probability, you don't have to have that like this, but I like to. We performed 5 experiments, so it's 5 trials, right? 5 draws, if you want to call it that, okay? So when it's experimental, you go back to the actual experiment. And how many 6 of spades do you have there? You've got 2 of them, so it's 2 over 5, okay? Let's do both of them as a decimal because I'd like to see that. First of all, 1 over 52 is going to be small, right? So as a decimal, 4 decimals would be 0.192, right? And as a percentage, that'd be 1.92%. So very small percentage of that happening. Very small chance. 2 over 5, however, is 0.4. That's 40% chance of that happening based on that experiment. But that's such a small experiment. It's not even close to being accurate, right? So that's one thing you need to pay attention, that they're different. And why are they different? It's because of the slow sample size, right? This is due to the small number of draws, or or you can actually say sample, okay? It's due to the small sample, okay? The theoretical probability, TP, is going to be more accurate in the long run. If the theoretical probability wasn't accurate, folks, casinos would be out of business, right? They base everything on theory, like especially deck of cards, all of that. Like they know their probabilities, and it's all based on theoretical, okay? All right. Last time I checked, they're doing pretty good. 30. Let's go to 30 and just do a couple there. Page 30. So you've got the spinner and you've got the results, right? These are the trial results. Let's call it that. Trial results. Okay, so this is going to be for experimental probability, and we're going to use this every time it says theoretical. Okay, we use the actual thing that was used to perform the experiments. Okay, the experimental probability of orange. Okay. Experimentally, which we're going to use these numbers right here. Get our total here. The total is, anybody did the math already?
Yeah,
60?
Yeah.
I usually come up with numbers that add up to a nice round number. 60 trials or spins, right? So it's going to be out of 60, and orange in this case is 21. Let's turn that into a decimal as well. That's 0.35. Especially when you're comparing, I'd like you to turn it into a decimal if there's ever a comparison with another one. State the theoretical probability of orange. So theoretical probability of orange, remember it's theory. What should happen, we go back to the spinner. And it's 1 out of 4. That's it, 0.25. Theoretical probability of purple. Okay, so just TP of purple, and we've got 1 out of 4 again. Okay, this one should be pretty straightforward. Experimental probability of purple. That's 7 out of 60. It's way off, right? It's not even close to 0.25. 760. That's 0.1167 if you round it to 4 decimals there. This one is 0.25. So not the same, right? Here's another one. If Rihanna were to spin it 950 times, how many times would you expect it to land on blue? Okay, we're going to use a prediction, and that would be 1 over 4. We use the theoretical times 950. That gives you 237.5, which is approximately 237 or 238 times. Okay. So there we go. That concludes this page. Let's keep going. I'm going to skip a few there. 31 probably threw you off a bit. I don't know. There's just too many numbers there. So Neil tossed a six-sided die and recorded the results below. So this is trials. Okay, trials. So this would be you would use this for experimental probability. Okay, every time it's experimental probability, you're going to come back to this chart. What's the experimental probability of rolling a 6? The number 6 was rolled 18 times. Okay, 18 times. So we know that the top number here is going to be 18. What is it? 90? Okay, so I'm going to go total is 90. Okay, so I know that the denominator should be 90. That's it. We just leave it like that. The theoretical probability of rolling a 6, do not look at this. You will look at I can do this. Okay. There you go. Anyways, you'd say theoretically it's 1 out of 6. Yeah, it's just that. Like you use this to perform the experiment. Which number has the experimental probability that matches the theoretical? So you basically, like, when is this approximately the same as this? For which number? I don't know if you did the math here. But this is what I would have done. Okay? I just go 13 divided by 90. This is 0.14. 15 divided by 90. This is 0.16. 14 divided by 90. This is 0.16 as well. 12 divided by 90. Sorry. 0.13. 18 divided by 90. 0.2. This one is also 0.2. So these are the probabilities here. So these are all the experimental probabilities. Write that down. Experimental probabilities for every single number in this experiment. The theoretical probability of every single number, okay, write that down here. Theoretical probability of every single number is the same in theory. It's 1 over 6. What's 1 over 6? 0.16 and so forth, so it's 1/7 basically. 0.17, 0.17, 0.17, and so forth. It's the same for every number. So the one that matches fairly closely is probably 15. I probably rounded it incorrectly here. 15 divided by 90. Yeah, that should be 17, sorry, if it's rounded to 2 decimals. I'm going to highlight that one and just say, in this particular experiment, you would say the experimental probability of rolling a 2 matches the theoretical probability of rolling a 2. So it's just getting you to think a little bit, like going backwards, perhaps, right? But that's what happens there. I think I'm good here. Is the election one. Who wants to talk about that today, right? No, it's important. It's important, but go to 36, please. Go to 36 real quick. And highlight that way you know we talked about it. Effects on the sample size. There we go, there we go. Okay, let's see here. I should be able to ask you this, and the problem should be the same, and you should be able to say that there's something wrong with the sample size, okay? A large cafeteria that serves lunch to more than 400 people per day has 4 main dishes, right? There they are. I could go for some chicken chow mein right now. Anyways, at first, 10 people through a line, no one chooses a vegetarian dish, right? Of the first 10, no one chooses vegetarian. Therefore, the manager decided to remove the vegetarian dishes from the menu in the future. Is this a good decision? Explain your answer. You should see it's wrong. The sample size is way too small, right? 10 people, right? It's too small. So this is not a good decision. Not a good decision. Since 10 people is too small of a sample to make an accurate prediction. It's not a good decision because 10 people is way too small of an accurate, right? And especially if you consider 400 people that are served in this cafeteria, 10 is just way too small. If 50 or 60 people have, right, there's not an exact number, but you definitely want more than just 10. Okay. I'm just going to leave it at that. The other ones are basically the same thing. Okay. And if you want the exact answer, if you want a proper answer, it's posted on Google Classroom. Okay, all the way to 37. All right. I'm going to stop there.